Welcome to this video on temperature effects of reaction rate. At the beginning of the week we talked about the general effect that temperature has on reaction rate. Whereas the temperature goes up, we see an exponential increase in the reaction rate. We talked about collision theory and how collision theory can be used to explain the why. It's all about particles colliding to make reactions go. And so if we think about it, increasing the temperature increases the motion, the kinetic energy of the particles, so they're going to collide more frequently and with more energy as we increase the temperature. And then we talked about the activation energy and looked at our energy profiles. The activation energy is the energy required, that's that barrier we have to get over in order to get from reactants to products. So temperature is going to help us overcome that. All right, let's do a quick rundown of the collision theory that we've been working on this week. It tells us that for reactions to happen, molecules have to collide, and those collisions aren't automatically successful. There are conditions that have to be made. Number one, the molecules have to hit in the correct orientation. And once those molecules do collide, then the collisions have to have enough energy to overcome that activation. So Arrhenius did some work to kind of map out mathematically speaking, what this relationship looked like, how it worked. And so you see here in the bottom of the screen the Arrhenius equation in its empirical form. It's not a very easy thing to work with. The frequency factor A is an empirical factor, so he gets that information from going to the lab and seeing where the graph intersects to come up with that. So we'll talk more about that in just a moment. All right, so just hitting some of the same topics again. You can't say it enough, it seems. So we know that the rate constant is dependent on temperature and is an exponential increase. I talked about before the collisions are going to happen more rapidly as the temperature goes up. We still don't have enough energy to always overcome the activation energy. And if you look at the Arrhenius equation, that factor E, the exponential function to the negative E over RT, is a measure of the fraction of collisions that have enough energy to overcome the activation. Now that doesn't make a lot of sense just written in words, so this picture here hopefully will help you understand that. So this is that Maxwell-Boltzmann distribution that we've seen a couple times before, and we see that at a low temperature, the blue line here, we have only a small fraction here in the shaded blue of the molecules that have enough energy to, when they collide, overcome the activation energy. And if we increase the temperature, we've seen in the past in our thermo unit that we're going to shift the distribution over to the right a little bit. We broaden the peak a little. And what that does is increase the fraction of molecules that now have that activation energy. So that's what temperature does for us. Now, a little bit more about that factor A in the Arrhenius equation, the frequency factor. We're not going to calculate it. There has been further studies done on it. We now know that it can be found by multiplying a collision frequency and then a steric factor together. Now, the steric factor is just geometry. It's how they fit together. That letter P there, the steric factor, has to do with the orientations. So the frequency factor overall is a combination of our requirements of orientation and frequency of collisions.
No, actually it says there the slope is negative.
Okay, so the form of the Arrhenius equation I showed you before, and I rewrote it here, is not that usable. It is an exponential function that we talked about. So to put it into a more usable function, let's get out of the exponential form and let's put it into a linear function. We can do this by taking the natural log of both sides. So we're going to get natural log of k, and then we'll do the natural log of this product over here. All right, using our law of logs, we're going to get natural log of a plus the natural log of e to the negative ea over rt. And like many of you keep forgetting, e and natural log cancel each other out. So we're going to be left with log of k equals the natural log of this frequency factor plus negative EA, which is our activation energy, over RT. All right, let's rearrange that just a little bit to get log of K equals negative EA over R. And I'm going to pull the T out just a little bit and have 1 over T. And then we're going to keep our natural log of A. So I've gone through this linearization here. Now we have an equation that's in the form of y equals mx plus b. And we've kind of graphed that out here on the screen for you to see the results of this. If I graph as my y variable the natural log of k, the rate constant, versus 1 over t, and yes, it has to be 1 over t, that's my x, I get a linear graph here. Now the important outcome of this is that from this graphical representation, I have a way to actually figure out the activation energy for a reaction. If I have a lab technique to measure rate constant, we do have those techniques. Of course, we have ways to measure temperature. I can go graph these two things like you see here, and now I know the slope of this is going to be EA over R. R here is the gas constant with the units of joules, so 8.314. So the slope of this line times R would give you the activation energy. A real quick and easy way to help us find activation energy for unknown reactions. If we take this graph and extend it back to the intercept on the y-axis, that is another piece of information we can grab from this. We can actually figure out the frequency factor A. And if we were interested enough in it, we could go back and find individually the steric factors or the frequency, the collision factor. We typically don't do that in AP. We're more worried about the energies of all this, so activation energy is typically what we're after. Let's do an example using this linearized form of the Arrhenius equation, and let's calculate the activation energy for a reaction. The problem I'm working is number 7 off of the class worksheet that we got and started on Monday. We did the entire thing in class with mechanisms, and we left the last 2 problems blank. Those are Arrhenius problems. All right, so given some rate constant data and some temperature in Celsius data, I wanted to see if I can calculate the activation energy. I want to create a graph similar to what we did with integrated rate laws, but before I do that, I need my temperature not in Celsius, but I need it in Kelvin. So let's create a formula to add 273 to each of those temperatures and get it in Kelvin. All right, so there we go. Next, we don't want to deal with just temperature. Remember, our x variable here is going to be 1 over the temperature. Now let's create another formula to get that, and that will equal our Kelvin temperature. Oops, I did not do that right, so backspace. 1 divided by our Kelvin temperature. All right, let's copy that down. All right, then I'm also not interested in the rate constant. I'm more interested in the natural log of the rate constant. So I want an equation for that. So let's input natural log, open the parentheses up, and I want A3 here. So close that down. Yep, they're negative numbers. So let's copy that down. And let's start making a graph. All right, so Excel, when you have data and you want to graph it, the one on the left is going to be the X variable. That's why I have 1 over T first. So let's highlight those and let's go to Insert, and we're going to do, once again, our scatter plot. And I don't really want to connect the dots. I just want to do a scatter. All right, so that doesn't look like much right away. Let's make it just a hair smaller. It should look fairly linear. It may not be perfect. Let's make it smaller still. All right, maybe we get everything going there. All right, what I'm really interested in now is the slope of this line. So let's go to our add trend line function here. We want to do a linear fit, and I want to see the equation primarily. That's really all I'm going for. I'm working under the assumption here it's going to be linear. But if we just want to do a quick check on is it really linear or not, I seem to have lost it, so we're going to have to start that process over again. Let's display equation and the r squared, and it's 1, so we really do have a linear function here. All right, now the important information from this, if I want to get the activation energy, here the slope of the line is negative 9515.7. That's not the activation energy, that's just the beginning. If I want to get the actual activation energy, I need to do some more calculation. We have to take the slope and we have to multiply it by R, the gas constant, 8.314. And so that gives me the activation energy in joules. Let's go back and relabel this. So let's just do E sub A in joules. And if we want kilojoules, energy is almost always given in kilojoules. Let's just do one more quick formula. Equals, let's take that value in joules and divide it by 1,000. So the activation energy for this reaction in kilojoules, if we want to do 3 sig figs, we can, is negative 79.1. Happy with my number? Because I'm not. What did I always say about the sign of activation energy? Yeah, it's always positive. So I have done something wrong, and I know that by knowing that fact. So let's figure out what step I skipped. What I did here is kind of dumb. I do it all the time. Probably the first problem every year I do this. The slope of this, the equation for this line is negative 9515.7. Now, if you go back to the Arrhenius formula that I gave you a few minutes ago, that is negative of the slope. And so what I failed to do was simply to get rid of that negative of a negative and make that positive. Just remember that your activation energy is always going to be positive. It's always an endothermic thing to have to overcome, and that's not a huge deal if you somehow calculated a negative, okay? That's just a graphical thing. So that was really all this question asked for. We could calculate A if we wanted to. We would just have to plug in, and remember our intercept is log of A, so if you take the intercept here and just the exponential function. All right, I'm going to pause the video now. I'm actually going to stop it now, and then in class we'll do more with the calculations and applying Arrhenius equation to find different Ks at different temperatures.